it is quite reasonable at this point in time to make the proposition that they indeed do occur. That there is, in fact, ample evidence that we have some level of nuclear activity going on. First of all, as far as neutrons are concerned, the object of most of, or at least perhaps the majority of the studies in the last 2 years, it seems to me that we do not yet have a definitive physics experiment that categorically establishes at the level of confidence that nuclear physicists are accustomed to. We do not have that kind of experiment yet that establishes that the neutrons in fact are a real phenomenon. On the other hand, it seems to me that we have so much evidence for neutrons that I don't have any serious reservations about their existence in these kinds of situations. As far as the tritium is concerned, in Provo, many of you may recall, I was unwilling to express any opinion on tritium on the basis that it was so unreproducible. I haven't changed my view very much, but certainly we have heard some evidence at this conference that there are more systematic results available now on tritium. And we should examine in this next hour how solid we think that extra evidence is. As far as the other nuclear products which have been expected are concerned, energetic tritons, protons and gamma rays, X-rays, and other things, even helium-4, I would venture to say that the evidence for them is exceedingly weak at the moment. Exceedingly weak. Now, on the other hand, we are faced with the situation where in many, many different styles of calorimeter, we have excess power apparently appearing. I find it very hard to prove to myself, or to my own satisfaction, that any one of these experiments is actually giving us the right answer. On the other hand, it's very clear that a large number of people have done very careful experiments, and they do claim to see excess power. These events occur in so many different complexions and configurations and different styles of calorimeter that it seems to me to comprise a fairly large circumstantial, perhaps that's not quite the right word, indirect level of evidence that the excess power is probably real, wherever it comes from. The real issue is the question at the bottom here. Is there any connection between these two sets of phenomena, each of which perhaps we are coming to feel more comfortable about? And that, I think, is the real question that we have to address in this round table. Now, as far as the aspects of the problem, which, to my mind, you might call the pro aspects, the items that tend to support the idea that we have got excess power with a nuclear source. To begin with, it's clear that when we work out the excess energy, some people have a very small excess power, relatively small, a few percent, 10%, 5 times their uncertainty, whatever it is, but certainly not an overwhelming amount of excess power. And they have to integrate over a long, long time in order to get up to their stated quantities of megajoules per mole. The kind of quantity that we would feel is at the borderline of chemistry, and if we get a lot more than that, then we think that we've got to look for a different explanation. Now, I have a lot of problem with this kind of evidence. It seems to me that it is intrinsically weak. It's intrinsically weak to say that because I can't explain something one way, I have to explain it another way. That there's something about that statement which seems to me falls far short of actually finding real nuclear products that we can correlate quantitatively with the heat. Now, when we integrate over a long time, obviously it seems to me there's a lot more opportunities for things to go wrong. I don't know why, but if excess power is only a few times the uncertainty levels, then I have some concerns. Now, there are a few very fortunate people, and we have 2 of them right on the podium here, who are in a more fortunate situation. They don't have to do this over anything like such a long time. They have so much power that they can say with much more confidence that it quickly adds up to a very large amount of heat that's hard to explain. I think they're in a stronger position. I'm still left with my intrinsic concern about this kind of argument for nuclear sources. I would rather say what it means is that we have a problem that we can't explain, rather than impute a nuclear origin. Now, the quality of this evidence is, in my opinion, so what I've said so far about this situation is kind of the intrinsic aspect of the problem. What the actual situation is, however, in this case, Liao here has only 2 experiments in which he finds these embarrassingly large quantities of heat. And he's failed to reproduce this situation recently, and it's probably not his fault. His electrodes keep falling apart, so we hope that soon he will be able to solve that problem and improve the statistics. But the fact is that right now, in my mind, we cannot claim very much from this experiment in support of a nuclear source of the heat, even though it appears to be very large. He also has we have to say, a strange-looking calorimeter, and he's putting in oodles of electrical heating to his furnace. We feel, I feel a little uneasy about that. The power gain of 20 excess watts over 2 electrolytic watts sounds fine, but he's putting in 60 or 70 electrical watts. And to his great credit, he is among the first to acknowledge these difficulties and is working hard to do something. Pons is in a much better position. He showed us in his presentation that his situation is reproducible. And not only is it reproducible, he's actually reproduced it a dozen times, maybe 11 times for sure, maybe more. The problem, of course, in this instance is that we only have Dr. Pons' statements about the situation to go on. We do have the independent review of the data, and the report on that was comforting. But one aspect of reproducibility that makes it such a powerful tool in the hands of scientists is that it makes evidence publicly available, publicly viewable and obtainable. And while the Pons-Fleischmann effect is concealed behind patent and proprietary considerations, it might as well not be reproducible because the rest of us can't reproduce it. So I believe that is an intrinsic, basic weakness, and it is a very big weakness. Now there's another problem as well, and it's common to the heat situation. I don't believe that it is at all easy to prove that this excess power exists on the basis of calorimetry. Simply because all you can do is stick a thermometer here and a thermometer there and do it a couple of times and some calibrations. You're faced with the fact that all you can measure is some temperature differences, basically. Now, we know that most of the groups working in this field have studied neutrons and tritium. Some have studied charged particles. One of the benefits of looking at a real live particle is that it is a real live thing. You can measure its time structure and time correlation. You can measure it in many different ways, not just with different and redundant diagnostics, but you can actually measure things about it that depend on very fundamentally different properties of it. The detectors work in different ways because this thing does something fundamentally different under different circumstances. It can scintillate in one instance, it can slow down and give you different kinds of scintillation after that. You simply can't get any other way. We don't have that with calorimetry. And it seems to me that an individual group, like Pons and Fleischmann, have the benefit of being able to study their apparatus for 5 years perhaps. They can get very confident through the solution of their apparatus that they have excess power. I'm convinced that they can become that confident. But I absolutely believe that it is probably almost intrinsically impossible for such a group then to convince any other group that is truly skeptical that what they're saying is correct. It's a very, very difficult problem. And it's made impossible when we don't have a reproducible phenomenon. If it's reproducible, then of course the total picture is completely changed. Calorimeter, you can use several different kinds of calorimeter. You can make the thing work dozens of times, and you can this way and that. You do all the things that an experimentalist needs to do to get himself comfortable. But I think that the fact that we can't do that with Pons's claims right now is a fundamental weakness, and it won't go away until that situation changes. And of course, I want him to say something about this in a few minutes. Now, the question is, does the excess energy correlate with helium-4? Dr. Miles says that it does, and he gave a very good account of his experiment, and he gave a very good explanation for some of my putative criticism. It's kind of interesting that if he's right, then we get kind of a big bonus with this particular result, this particular experiment, because it does everything for us. You know, it not only confirms the heat. See, if he measures all this helium-4, we're pretty confident that he can't get helium-4 unless he's involving an MeV energy scale. And it correlates kind of nicely. It also establishes the nuclear source. It does constrain the number of possible nuclear reactions that can produce it. It will constrain the theories. And I think it also, in his particular case, with his result, suggests that this reaction has to take place on or exceedingly near the surface. And it also indicates that, even given that, the energy of helium-4 has to be extremely low, the kinetic energy. Somehow this MeV scale of energy has to be distributed some other way. If that were not true, then he'd find half of his helium in the electrode. We find their helium. There must be some with these heat experiments in electrodes, and they haven't done. So that would be kind of cute. But I think right now the actual situation is we've only got one series of experiments. We have concerns about the controls, whether they're real controls, whether the samples were processed the same way. Well, we know they were not. We have concerns about the amount of time that the controls and the test samples were exposed to what turned out, I think, to be different sources of helium-4 at different pressures for different times. We have a problem with whether it's nitrogen or hydrogen or deuterium in the pot. And I think what this means is that we obviously have to work very hard to do something about that. I'm sure he's going to say something in 3 minutes. Now let's leave this thing, this last one here, because I'll come back to that in a moment. Against the idea of heat. Now these are not fundamentally contrary items, but they have been used in the last 2 years to suggest that this heat just simply can't be right. First of all, the regular expected products, obviously we know, they fail catastrophically to account for the heat. We know that. Whether this is a catastrophe for cold fusion or a catastrophe for nuclear physics remains to be seen. Similarly, the tritium and the helium-4, so far at least, when people have looked for it, apart from Dr. Miles, doesn't seem to come with the heat. Bockris measured some tritium ones that seemed to come with the heat. And he also got within, I think, maybe 2 orders of magnitude of the right heat, but that was only once. And he's measured plenty of heat on other occasions, and there wasn't tritium. And so have other people. We'd expect gammas and X-rays, and they ain't there, it seems. Hardly there. We have the energy problem. And we also have something which I think is a little dubious, but the conditions for getting the heat and these other products don't seem to be the same. Now, I don't find it easy to put my finger on exactly what's different about them, but I think there are some suggestions from the data that the neutrons don't have to have the same deuterium metal ratio as the heat. Probably much lower. We've seen it in different stages of electrolysis. We get discharging deuterium from a metal, and so on. Sometimes after we've discharged most of it. The current density seems to be different. Sometimes you get neutrons where there isn't any current density, in the titanium deuterium gas system, for example. And we can talk about the surface volume. These conditions are just different. Now, of course, the problem with all these contrary events, apart perhaps from the item 4 here, is that if we were willing to abandon our standard views of nuclear physics, all these other things would go away. Okay, we wouldn't really have much to go on. We'd say, well, these conditions look different, but then we'd say, these are very complex substances, and we don't understand anything really about what's going on yet, so maybe these are not problems at all. That's where this little comment back here comes in. Curiously, the fact that the neutron-to-tritium ratio is all wrong by a standard view, in a sense, is a kind of a boost for the idea of a nuclear source of heat, because it alone demonstrates that the nuclear products, in which I said earlier we can have a lot more confidence than anything else, are not standard physics. Okay? In which case, it demolishes the other 3 or 4 points that I just had up, which were all nasty things for heat. Well, that's all I have, really. Actually, I have some more things, but I don't want to show them. Not yet, anyway. What I'd like to do now is to invite our panelists, Dr. Pons, Dr. Ikegami, Dr. Miles, Dr. Lee, and Dr. Liang, to comment on this general topic, either specifically on the points that I've raised, or to express their own first thoughts on these things. And I guess I'd like to stand to start.
First, your points are well taken, Dave. I appreciate everything that you said. I just want to go over a couple of things that's guided our research and a couple of thoughts that we've had during this entire episode, this entire project. And first of all, is the fact that more and more people, I think, admit, okay, so there's some heat. And you're right, there's a nuclear origin, or is there not? But first of all, you have to come to grips with the fact, is there any excess energy or is there not any excess energy? And our definition of excess energy is the situation that arises in our cells when we have considered all known chemical or physical processes in the energy balance. In other words, there is no chemical reaction or other physical process going on in that cell that is responsible for the excess. If you know all of the chemical and physical processes, then you still have an excess. And what is the excess due to? And we maintain that it is either of nuclear origin, an unknown nuclear origin, or a known nuclear process. Because just from the fact that you have excess energy means that you have excess energy over and above any physical process that you can account for. And those are simply supported by the blank experiments. We take all of these factors into consideration, and we don't know of any other physical process or chemical process that we can use to explain it. So that's the first point. If you have excess energy, where does it come from? We can think of no chemical process or physical process other than the ones we've mentioned from which it can arise. So that's the first point. The second point is we have always done all of our measurements in the calorimeter, which we put up 1,000 times. And the response of that cell, the response of that cell as a function of time, the temperature response is given by this very simple equation. I apologize for that, but that simply is the response of that cell, the temperature time response of that cell. We've gone over many times the approximations we make to derive the excess heat, which is given by the QF term, wherever it lives, right here. And we make our measurements, we solve these equations, and it is not true that we have not given this publicly in our large paper last year. This is the overall equation. We made a simplification of this, of course, in the paper that appeared last year. But still, using this equation, both for all of our blank solutions and all of our active cells, we obtain an excess heat. And so I don't agree with that. I don't agree with the statement that these have not been available, that we've been constrained to secrecy. I don't agree that people have not had this analysis to hand or the capability of making the same sorts of cells. Nor have I seen anyone take the time dependence of the cell into account when they try to make their thermal balances. I don't recall seeing any paper where the total time dependence, where the total energy balance has been made over any significant period of time to determine the heat output. And that's been the basis of our entire analysis forever. So the method has been available, the materials have been available. Nobody has criticized this analysis with their own data. They've criticized our analyses with our data. They have not come forth and treated the entire response of that cell to their data as far as I know. I just have not seen that. So I don't agree, indeed, that it's true that people do not have the facilities in hand to reproduce our results. We have not hidden anything. We have told them everything up to date. On the other hand, I do admit that we are doing other things, and for us to not come forth with that sooner, like the alloy electrodes with other things we're doing, I think that would be a very big mistake for one simple reason. The reason the worldwide resources now for research in this area are limited. And for us to have an idea that we're trying now and say, oh, this looks good, and for you to run out and waste your funds, the precious little that are left now, on an idea that we're not sure of yet, I think is a mistake. So, yes, we have new things we are trying, and we will report those in due course. But I do not believe that people who follow the analysis that we have made and try the blanks under the same situation, I don't see that they will get significantly different results than we reported. Now, having said all that, all this aside, we know that it is in the end, it's going to be incumbent on Martin and myself to bring this thing as far along as we can, and it will require a device, a tabletop device, to sit there at 10 degrees or 20 degrees or 50 degrees above room temperature for months on end without any apparent, and all that clearly due to an excess. We realize that, and we are trying to do that. And hopefully we're well on the road to do that. But just in my mind, if you admit there's excess heat, then you should come up. It's incumbent on you to come up with an explanation, if you admit there is excess heat, as to what other process this may be due to, if it is not nuclear. I just don't see that there's any known chemical process that could answer any excess heat at any level, unless we missed, some simple chemical reaction in our cells. And the only thing I can say in defense of that is we've always added liquid to our cells, solvent to our cells every day. I think we've more than compensated for any possible recombination reactions. I don't think that there's anyone now that really thinks that there's chemical recombination. We've weighed our cells at the beginning of all experiments, and at the end of experiments, there's no change in the mass of the cell, the total mass of the cell, and it's just very difficult to believe that these things are based on a chemical reaction. So if it's not chemical and it's excess at all, then what is it? I agree with you. And we do not have a good theory for it. We cannot explain it on conventional nuclear reactions. I agree with that totally.
Thank you.
It's really hard for me to tell anything about whether it's cold fusion or whether we really have excess heat, because so many important key parameters are missing in our experiments. And there are so many important things that I really like to know. For example, as for the excess heat, having some excess heat from how we can tell 100 watt from cubic centimeters. And we have to find out whether it's a surface effect or volume effect. That is the thing. We have to move in that experimental condition. And so it's good to have some volume and get some energy, but also we have to know the surface. And what about surface effect? It's nothing to do with surface or volume. And this is also related to neutron emission if there are real neutrons. And also, I'm always having some doubt about number two, possible recovery of endosonic energy. And if somebody work as hard as we do on heavy water or deuterium by using the same experiment by using light water or ordinary hydrogen, somebody might have excess heat. That's the easiest way to find out whether it's a nuclear origin or not. And I think we are almost reached the beginning stage of the experiment. Now we have to find out what are the parameters and what are the things that we have to control. We have to get into that region, experimental region. So somebody must work on what we saw by using light water or hydrogen. If we work on that as seriously as we do heavy water or deuterium. And as to the endosonic effect, there's the data, and palladium is certainly strange material, and up to this point, we have data, but I've never seen the data up in this region. So if somebody says we have to go to the atomic ratio to 1, then what sort of energy we're supposed to have? And if hydrogens are dissolved, then they must bring out some energy. And what are they? Are they comparable to the energy we observe, or they are really illusion? That I really wanted to know. If somebody knows that, I'd like to know the answer. And also, as to the neutron, I myself is almost quite sure we are detecting neutrons, but I don't know the origin mechanism. So that could be some mechanism, but surely I think we are detecting neutrons. And the important thing is sometimes they say it's above background 10% or 20%, or somebody said 10 times. But really, it seems to me to really depend on how you choose dwell time and how you choose dwell time properly, just considering detection efficiency, overall detection efficiency properly. And then, for example, in our case, we detect the neutrons in a very convincing way. Burst of neutrons, something like that. But it's a real time of 100 seconds. But if we, average out those signals for 1 hour or 30 minutes, it's really nothing. So somebody said we detected the neutrons only about 5% of background or so. But it's not proper way to detect neutrons. So that we have to find out what is the proper choice of dwell time and efficiency. And the third is, I think we have to really know some parameters. By having neutrons or hydrogens absorbed in it, what will be the number of electrons that flame starts? Or what sort of microcrystal size we have in palladium? Or is there any possibility of hydrogen being excited to a certain level? I mean, quantum numbers, say 5 or 10 or whatever. I think, we've been working, probably we will soon know the atomic number ratio or energy spectrum that we know mostly, and also by controlling many things, we probably know the source. In our case, by adjusting the efficiency, total efficiency, we try to find out the source. I think we know we succeeded in it. Those things, probably we are now the stage of those things. I'm trying to see the mechanism of it. Otherwise, we keep staying in a very preliminary stage. That I don't like. finally, what I think of the relation between nuclear effect and excess heat. At present knowledge, so far I done, is still this stage. Just really, ice blocks from the Antarctic contains compressed air measured to penguins' droppings. And if you make Western water by using that ice cube, then that produces bubbles, and also at the same time produce cool. Then, seems to me at present, I don't know later, but at present we are discussing what is the relation between bubbles and cool. How we can tell? And knowing further into that is our task. I'd like to know your comment on this.
Thank you very much. Let's move on to Dr. Miles. I want to say just a few things about excess heat. The main thing I want to comment on is how we're healing. Like I mentioned yesterday, early on we did not get excess heat. In fact, we didn't break even. We got less heat out than we put in. So we had to learn how to do calorimetry carefully. And when we did that, for 5 months, we were just breaking even, basically. I think the important thing is the electrodes have to be arranged correctly. The plate and electrode needs to have the counter electrode very symmetrically around it in order to get the excess heat effect. At least that's what our experiments seem to indicate. And anyway, since we started doing it that way, we've had 7 out of 10 experiments give excess heat in heavy water. It doesn't work all the time, 70% is pretty good. And in regular water, light water, we've got excess heat 0 out of 4. So that indicates there's really something different in heavy water than in light water. And again, I don't see, even though the effects are small, maximum maybe 30% excess heat, over a long period of time, this is still hard to explain by a chemical process. I've tried to do it, but I can't come up with a reaction that will explain it. Now going on to helium, why we decided to look at that is people were looking for neutrons and not seeing very many. They've seen some, but very little. And tritium and maybe gamma. If there's really not very many neutrons, not very much tritium, what are you left with? It almost has to be helium. We were hoping helium-3, then we wouldn't have so much controversy. We found a lot of helium-3, but helium-4 is what we found. I'd like to stress that we did control experiments in regular water. And these are done exactly the same way. We use exactly the same system, exactly the same electrodes. We shipped them the same way by ground transportation. They were analyzed at the University of Texas in exactly the same manner. And they did not show any helium. And that's hard to explain why helium would know exactly when to diffuse in the glass and when not to diffuse in. That's hard to explain. I don't see anything that we did different that would account for us seeing helium in the G2O experiments, not in the H2O experiments. The question's been raised whether we had helium in the palladium rod. You can do a calculation on that. And, the most helium that you could possibly have would be 1 part per million. Well, we have 10 to the 22nd palladium atoms, so that would give you 10 to 16 helium atoms. That may account for a few days, perhaps. That could not account for our almost 70 days of experiments and periodically, whenever we have had excess heat, we had helium. And furthermore, since we did the experiments, we sent the original palladium rod to Rockwell, and they did analysis on it. And the amount of helium in our original rod is less than the detection limit. It's very, very small, much less than 1 part per million. So the helium could not have come from the palladium rod. And so the only other question is come from the atmosphere. I tried to answer that yesterday, that the only way to come from the atmosphere apparently would be the diffusion through glass, but there
our experiments, our control experiments show that in the water experiments with H2 present in the flask, we did not see helium. And so it did not diffuse into the flask, but the flask was filled with hydrogen. So hydrogen, like I said yesterday, apparently blocks the helium from diffusing in, since they have to go through the same sites, they diffuse by the same sites in the glass. And you do a calculation, you have 1,000 times the number of atoms of hydrogen diffusing out, and you have helium diffusing in, because there's so much less helium in the air outside. So you've got a stream 1,000 times greater going one direction that the helium has to flow against in order to get in. And furthermore, Pons in the 1920s, late 1920s, showed that hydrogen will displace helium in the glass. Therefore, I don't think the helium stands a chance with all that hydrogen going the opposite direction. It doesn't stand a chance of diffusing. The only way to really answer critics on this, however, would be to do it in stainless steel. We plan on doing that, not so much that we're concerned that we're wrong, that we think it won't make any difference, but at least that will satisfy other people that what we're doing is right. Another reason we want to do stainless steel is we would like to quantify the energy. How much energy do we get per mole of helium? That's going to be a very important experiment. That will tell us something about the energetics of the reaction. And it would be nice to get a lot of different points, a lot of various excess powers, and a lot of points with helium. We need a very accurate helium measurements, better than we could do at the University of Texas. And we have that by a commercial company now in Texas that does this all the time for a living, analyze helium in natural gases. So that's all they do, is analyze for helium. And they use a GC, which will separate the D2 on a time sequence from the helium, so that the helium will come out faster than the D2, and so they can separate before they do analysis of the helium from the D2. And they've already done one analysis for us, and they get the results to two significant figures, where all we could get was order of magnitude. They can give us parts per billion in the flask, to two places, parts per billion. And they've already done this with us just a few weeks ago on a flask that I mentioned yesterday that we prepared by the spot method by co-depositing palladium and deuterium simultaneously and getting excess heat. And we sent that flask off for analysis, and with 0.14 watts of excess heat, that corresponded within a factor of 2 of the energy expected for the D plus D reaction, which gives you 23 MeV. So on the basis of that, we can say already, assuming we haven't made any errors, which I don't think we have, we say that the energy of the reaction is greater than 10 MeV. We can't say exactly what it is yet, but we can say in this day it looks like it's greater than 10 MeV per mole of helium. So that helps pin that down. We want to pin that down exactly by doing further experiments. And we hope other people will try to do these experiments, because we don't want to be the only ones reporting helium-4, because we need other people to support this finding. And the University of Utah, the Pons cell, very early on in 1989, were analyzed for helium, and it's only a paragraph or 2 in Journal of Physical Chemistry, but they detected helium-4 coming out of their cells. If you go back and read the paper by Wallings and Simmons, and what the amount of helium-4 they report is very similar to what we're finding. So it's not just us alone that's reporting helium, it's the Pons cell early on, and I hope other people will do similar experiments. And by using the spot method, where you co-deposit palladium and deuterium, you can get excess heat quite reproducible. And you can get it fast. In fact, I just got facts today from Ben Bush, who still worked in China Lake in California. He said he started a new experiment where he ran the cell in reverse for a while to get everything in equilibrium. Then he added a little bit of palladium chloride, switched the current direction, and he had excess heat within 2 hours. So here's a case where excess heat showed up within 2 hours when you co-deposit palladium and deuterium. So with that method, I think other people now can get the excess heat effect easily and quickly, perhaps, and start doing analysis for helium and support what we have found. And with that, I'll conclude. Thank you.
Thank you very much, Dr. Lee.
realized that being a panelist, just sit here and to answer the question from Dr. Worledge, it's too difficult for me, because this means I should understand more. But I'm not in a situation like this. As a teacher in the university, I know that propose a question is easier, answer the question is more difficult. So I selected either way. I try to propose some questions also. But I think sometimes if you ask a good question, you will be closer to the truth. In my research group, the experimentalists like me because I always ask them the questions. They like me to ask them the question. So what's my question? It seems to me very strange now. We are from all over the world. We didn't discuss before, but we are working for the same purpose. But we always come to very similar answer. For example, the first, a lot of people try to detect the gamma ray. Then what's the answer? A lot of people didn't see gamma ray. So for this question, most people answers no gamma. The second question, a lot of people use palladium, a lot of people use titanium for various reasons. Because palladium is more expensive, for my case, I try to use the titanium. But for some people, this is not really a reason. We always use different materials, but we come to very similar answer. In your experiment, you feel palladium is better or titanium is better. As my feeling during this conference, last conference, always the palladium is better. The third is for the neutron detection. In my country, this morning I talked about the neutron spectra. Looks like this, qualitatively. We obtained only once. We couldn't reproduce it. But all over the world, I believe we see this kind of spectrum once and once again. Why it's not in other shape? For example, some peak here, some peak there. No, always similar. So for these three questions, the answer is yes. For three of them, what's the probability? It's very low, but seems we are always answer yes. I'm teaching the statistical physics in the university, so I always use the probability. Now, one more probability happened to me also. You see, in my mind, I always try to nail down something in experiment. I try to fix it, nail down, then I can start my theoretical work. My feeling is it's very difficult. But once I heard from Professor Melov a very interesting topics. He said, if you try to nail down something in experiment, what's the sensitivity? For example, the neutron. If you try to detect the neutron, or you try to detect the tritium, or you try to detect the heat, you are supposed to use different method. For the neutron, it's a nuclear method. For the tritium, you are using the chemical method. And for the heat, you are using thermodynamic method, calorimetry. So at the time, if we use the conventional theory, just think of the DD reaction with the conventional branch ratio, then the sensitivity ratio is very large. If neutron is 1, for the tritium is 10 to the minus 9. And if you use dynamic method to measure the heat, the sensitivity is 10 to the minus 13, very, very low. At that time, select an approach, it's not neutron because we do not have sophisticated measurement. We didn't try to measure the heat because we do not have very good calorimeter. We tried to find the tritium. At that time, we didn't know we are going to measure something like alpha particle. We tried to find the tritium. Then we use CR39. This morning, fortunately, I had lunch with Professor Freshman and Reparata on the lunch table. Professor Freshman said the helium-4 is most easiest one to detect. Professor Myers said it's very difficult. You have to find a lot of difficulties. Then you can go to the right answer. But from Professor Freshman, it's the easiest one. I do not quite understand, but by fortune, we just hit this one. So for me, go to the answer. What's the origin? Excess heat. What's the origin for this excess heat? My answer is right now, I don't care. Yeah. Because for me, I try to nail down the physics, the new phenomenon. Is there really any anomaly? I try to nail down this phenomenon. I understand one point. If more people are involved in this, we have more chance to answer this question. So I didn't keep any secret. I opened to all over the world. Let them know what we are doing. Then we have better chance to fix is there any anomaly. Once we see the anomaly, if it's fixed, we can use this to find any source. That's my answer.
Because we have to get a much better record of what we have done to our electrodes. I suspect that very many people who've had very poor results have used pieces of palladium over and over again. And in fact, many of the statements in the literature about the behavior of palladium specifically are concerned with measurements which have been done on old samples, and goodness only knows what's happened inside the lattice. The other point, of course, is that one of the things which is so awful about the field is that there is virtually no electrochemical kinetics. With due respects to what John Locke has said, really, it's a drop in the ocean which has been done. And if you go away and have a look at the electrochemical kinetics and the relationship of the surface properties which you can determine electrochemically with, say, just the charging ratio, then you will very quickly come to the conclusion that Professor Schlottbach was absolutely correct. And that is that palladium hydride, I define palladium hydride these days as the electrochemical equivalent of a cow pump. It will take down just about everything. And until that is got under control, you will have irreducibility forever. And that may mean a radical redesign of the apparatus so as to exclude components other than palladium. It will be unpleasant to have to go through this redesign procedure. But if you want reproducibility, study electrochemistry and have a look what's on your surface. You will be astonished.
Of reproducibility of results. There is an issue of reproducibility of obtaining the same experimental conditions. What you have to do simply is understand what are the important conditions, control them, and measure them. Always experiments reproduce the same results if the conditions are the same. It's as simple as that. I'd like to thank Dr. Worledge, in fact, for explaining something which has been confusing me for a long time. When I first met Douglas Morrison, in fact, 2 years ago, he said to me that he was a skeptic and that I wasn't. This was confusing to me because I always thought of myself as a skeptic. And David just defined a skeptic as a person who could not be convinced by Stan and Martin's calorimetry. By that definition, Douglas is a skeptic perhaps, but I certainly am not.
This is the first time I believe the second. As a nuclear physicist, I am not satisfied in the state of art in from nuclear point of view of measurements. It's not, we didn't reach the same level of confidence in nuclear measurements that it has to be, but we're approaching, and this is good. And as a believer, what does it mean? I believe that if we have some question from nature, we definitely has to answer questions. And maybe this phenomenon exists, maybe not, but now we have a question and we have to give an answer. This is our responsibility. And the last point is that it seems to be now the situation is not such that we have to say that there is strong contradiction between something and something. The experimental situation seems is unclear, to say anything naturally. And the last point, the very last point, is that there is no any tragedy in this situation, because before we had to wait for 25 years before the neutrino was discovered at its prediction. Another example, the famous experiment in solar neutrino takes 20 years and still it is going and it's okay. So we have to work hard and we have to convince ourselves that it is we have good opportunity to enthusiastic people to work. Don't say that they are crazy, they are doing pathological science. Now it's an open question.
Thank you very much.
Chips of titanium, found four or five that were active shown by gas radiography. I'd like to ask the panel, would it make sense before doing further gas loading experiments with titanium to do as Srinivasan's group did and try out the gas chips first and select those that show some evidence of having nuclear reactions?
Who would be interested, Dr. Lee, what do you think about the idea of screening materials by doing some kind of, let's say, radiography after loading them to select the ones that show activity, collecting them together in a little pot, I imagine, and then doing the experiments on that sensitive material?
In fact, this time when I come here, I look around and around, I try to find Dr. Srinivasan. In fact, in my university, we have a plasma focus device, the energy of which is 200 kilojoule. And Srinivasan's plasma focus device is about several kilojoule. So we try to reproduce his result, and in fact, I discussed with George Meyer. He is going to do. So we try to work hard, and we try to have something to make everyone confident.
Maybe I should add that there is a value in this plasma focus thing. It seems to me it's quite conceivable that one could make the electrode with lots of different alloys and materials in a flat sheet, and so you do one series of runs, and then you can test the whole lot, and you can pick out the ones which look as if they're active. Seems to me that could be a very good way ahead.
I would like to ask Dr. Worledge and Dr. Pecoraro if they would agree on the following summary of the status, which was proposed by Eugene Maloff. He said he would describe the evidence today as overwhelmingly compelling but not conclusive, and he said that he did that because the word conclusive is reserved for an intimate blend of theory and experiment which has not yet taken place. And my personal opinion is I can't think of any theory that has made a quantitative, non-obvious prediction other than the nonlinear effects of dependence on current and temperature temperature predicted by Robert Bush and observed in his calorimetry. And I think it's in that direction that conclusivity will be obtained.
I'd like to thank the panelists and certainly to thank you, the audience, for such a fine set of questions.
And we are supposed to talk about the future. And we have here Bob Huggins, who hasn't spoken at this meeting, Fitzgerald, who has, Michael Cooley, and Giuliano Caprata, who needs an introduction. Now, I thought that my colleagues will say a few things about different aspects, but I think the idea is, of course, to interact with the audience. And I thought we will divide our comments into two parts. We'll start with thinking about, say, next year's meeting and what we should have ready for that time. We should think about the development of existing approaches. And of course, we have neutrons, trichons, helium 4, charged particles, electromagnetic radiation. I hope that Dr. Will and Tara, where is the doctor? You're supposed to come and join us. Yes, I told you. You were supposed to come and join us. We're looking for your words of wisdom on development of what we should be doing to develop our search for products of reaction. Now, as regards the heat, we have to bear in mind that I think we want to link the heat to the products of reaction. We've seen the beginnings of this work during this meeting. And here again, I hope that Mike McCooley and Fitzgerald will talk a little about that. And theory, I hope that Giuliano might stimulate some further interaction with the audience, but I would like to see some delineation on where the theories could take us to suggest experiments on the one hand, new experiments, but I think we should not get into a static situation in our approaches. What does any given theory, or what good theory, what developments of the theory do we need to suggest new experiments? And again, the converse question, of course, what do the theorists expect of the experimentalists in order to develop the theories further? Now, I would then like to go on to think about the development of new approaches. Now, I hope you will not be offended if I say that I think I have already mentioned this at this meeting, that in fact electrochemistry, the surface science and the solution chemistry is sadly missing from the work which we have been doing. And I hope that Michael Cooley and Fitzgerald will say something about that. And of course, I think that our consideration of the material science aspects is also fairly primitive. And Bob Huggins, I hope will say something about that. We have not heard very much about imaging, but probably Dr. Srinivasan was not here, but I'm sure that those of you who follow the literature are well aware of the work they and other people have done on autoradiography. I'm particularly pointing to the Indian work because, of course, they have sorted out chips of titanium which have generated tritium and said, well, these are the chips, by autoradiography, these are the chips which give us these effects. And I think this really makes a link back to material science, because I think we have a means at our disposal for sorting materials into have effects and those that have not, certainly on the basis of the tritium generation. And I think we could follow that. And there is, of course, a question mark here, because there are other imaging techniques which could be developed. We certainly have one in mind. I would like to know whether anybody else is thinking about that and whether they would share their thoughts. Now, number 7 is the question of doing new experiments. But at the end, I hope we have time, and it doesn't really matter if we do this in this particular order. These are just my initial thoughts. At the end, I would like to come to the question of adequate reporting. And here, let me just say that adequate reporting to me means that we should say in any paper presented at future meetings, the idea of the perfect experiment would contain information on the electrochemistry, surface science, material science, heat, products of reaction, time dependence, everything thoroughly characterized. But I don't think we would aim for that. I hope at the end of the day we could agree that in future reports we will always specify the hydrogen content of the heavy water, if this is what we do, or the hydrogen content of the deuterium gas. If that is the experiment we do, we will specify the deuterium to metal ratio, that people really will make an effort to characterize that. And last but not least, that they will report the history of the particular specimen for which they give data. I think we've been all terribly at fault in not giving the detailed history of the specimen. And in fact, I would say that much of the work which has been done on the characterization of absorption of hydrogen and deuterium and tritium into palladium has been done on very old specimens which have been used and reused. And if you ever start any work on that, you will certainly find in the first week that if you reuse a specimen, you get a different answer to the one you got on your first experiment. So I think the time history of the experiment is very important. And I'm sure my colleagues will have many things to say on all these things. So if you are agreed about that, we should start. Are you all happy? We start with thinking about the further development of the work we've heard today. Yes? Shall we start with that? Maybe if you spill over into consider our aspects, so be. So, I don't know whether Dr. Lill and Dr. Taraf would like to say something about what they can foresee or what they would urge us to do in further characterization of the products of reaction and then over to the audience.
Should we have two kinds of information because I know that. Microphone? So we have two